this week we're going to be talking about writing functions for the first time. And so I've decided to call this parts 1 and 2 because it used to be spread over 2 weeks. And now since this class is only once a week, it's or spread over 2 lectures. I guess it was all 1 week, but this is all 1 lecture now. So like always, timing is hard. I'm not 100% sure where we'll be with all of this stuff, but we'll try to get through it all. If we don't, then we'll get through it next week. So the agenda, I wanted to start out by reviewing the take-home midterm. I know not everybody is finished with it yet, and I think technically the deadline is midnight tonight. So if you haven't completed it, then I suppose I would ask you to just log off while we do that, and then you can come and review the recording later. But of course, I can't control if you're on or not. So that would just be kind of on your honor. And then we'll start to talk about functions. The main thing I want to talk about in this first section is just sort of the way that R works generally. And the big idea here is that literally everything in R is a function. Okay, the assignment operator is a function. The plus sign is a function. Everything is a function. Okay, so we'll talk about that. And then we'll kind of step away from that a little bit, from this sort of like overall sort of view of functions. And then we'll start to dig into what are the components of a function and how do you actually go about writing a function. And then finally, we'll finish with function workflows. Okay, so I know quite a few of you have at least dabbled in writing functions before, and that's great. And quite a few of you have never written a function ever before in your life, and this will be the first time, and it's all brand new. So, so wherever you're at with that is fine, but please do pipe up and ask questions if you need to along the way. When we're on Zoom, it's a little harder for me to gauge sort of how people are understanding what I'm teaching than when we're in person, because I can't read nonverbal cues as easily. Okay. All right. So learning objectives, understand and be able to fluently refer to the 3 fundamental components of a function. So we'll talk about those when we get to talking about the components of the functions. And then understand workflows often lead to writing a function, and then how you would iterate from interactive work. So you're working on something over here, and then how you would then move from that to, okay, now I'm going to abstract some of this work and just basically wrap the whole thing into a function. Okay. And then hopefully by the end of class today, you should be able to write a few basic functions. I'm not talking about super advanced functions, but like, for example, if I asked you at the end of class to write a function that subtracts the mean from every observation in a generic vector, I would hope that you, numeric vector, obviously, I would hope that you would be able to do that. Okay. All right. So with that said, we're now going to jump to reviewing the take-home midterm. Okay, unless there's any questions so far.
Yeah, I guess I had a question. If we like log off, is there like a time that you would like us to come back?
That's a good question. I don't know how long it will take. So you can log off and then maybe just pop back in 30 minutes maybe, or 20 minutes. 20 minutes probably a little safer, and just kind of see where we're at. If we're still working on it, then just hop out for another 5 minutes, 10 minutes, however far. If you log in 20 minutes and we're still on the first question, then it's going to be a little while. But yeah, otherwise, maybe if somebody else in the Zoom has your number, they could text you or something. That's my only other suggestion. Okay. Did that answer your question, Lana? Okay. All right. Hang on. Let me get this up. I actually don't have it up. I thought I had it up, but apparently I closed it when I was closing my other applications. Oh no, I do have it up. I just couldn't find it in my Zoom share. Okay. That didn't work again. Come on, Zoom. Okay. So for the take-home midterm, there was, oh, wait a minute. Oh yeah. So this is just some stuff that I was doing at the start. This is not really very important. I set my theme up here. So I set it to theme minimal, but then I added all this additional stuff. And this is mostly just because of the theme that our website is. And so, yeah, not a big deal. Okay, all this is background stuff. So then we get to the first part, part A, 20 points. So we're gonna download the data. So the first thing I asked you to do is just run this function. So I actually gave this function to you and I just asked you to run it, right? So all we do is hit Command Enter and we should be good to go there. Then I asked you to use the function to download all the data from 2014-15 to 17-18. Okay, so I'm starting out by loading the tidyverse because I know I'm gonna need that anyway. But if I go download file and I say 15, right, it should go out to ODE, the Oregon Department of Education, and download the data for 2014-15. And it does. You can see the academic year there, right? Similarly, if I go 16, I should now get equivalent data for 15-16. And you can see, indeed, it does. Okay, so all I need to do to get all of the data is just loop through a vector that has 15, 16, 17, and 18, and apply this download file function. Okay, so I do that. It takes a minute. And there we go. It downloads all the data. So now you can see we have 110,000 rows and then almost 111,000 rows and these 21 observations. This code is applying this function to each of these integers, right? But I could just as easily have written this like this, right? 15 to 18, and then say, put the tilde, and then say download file .x, right? Those are the exact same things where the tilde fills in for function.x, right? Another way I could do it is instead of using the tilde, I could say function year and then download file year, right? All three of these are equivalent. Okay, any questions on that? All right. Okay, the next step was to conduct some basic data cleaning to make your data file look like the following. Okay, so this is actually just how I did it. Let's look at the actual, let me get there real quick. Let's see what it was supposed to look like. All right. Hang on just a second. Okay, add to my share. Okay. Oh gosh. All right. So it's supposed to look like this, right? So we have the academic year, district ID, district, school ID, school, student group, grade level, and then number proficient. So all, and then percent proficient, right? That's how it starts out, right? But then we're going to do some basic data cleaning so it looks like this. So this is essentially just kind of moving it from wide to long. And so we have now academic year, district, school, and student group, which we have. Do we have student group up here? Yes, we do have student group. So all of that is the same. And then grade level, that is also the same, I believe. Let's look. Yep, grade level. Okay, except we've cleaned the names, right? Added underscores instead of spaces. But now I have this level and N, right? So for grade 3, there were 2 students in level 1 for Adrian Elementary School who were coded as Hispanic Latino in 2014-15. Okay, and so that's what we're going to do here. So I'm going to first just clean the names. So that's going to change like school ID to school underscore ID instead of school space ID, right? And then I'm going to select academic year, district, school, student group, grade level, and then all of these ones that have number in front of them. I could also say starts with number, but I just went ahead and selected each of them. And I think part of that is because we have number proficient, right? Which is level 3 and 4. So I didn't want to do that because I only wanted these ones, okay? So I just get the ones that have number in them. And that looks like this, okay? Number 1, 2, 3, 4. And then I'm going to filter where the student group is either white or Hispanic Latino. Okay, these are the two student groups that we're going to be comparing. And you can see we have a bunch of NAs. That's because the cell size is sufficiently small that we're going to omit it. So it wasn't reported. And then we're going to drop NA from number level 1. So if I'm dropping NAs from here, it's going to just remove the entire row for anything that's missing there. And if it's missing on level 1, it's going to also be missing on level 2, 3, and 4. Okay, so all of those should be good. And that looks like that. See, I'm not sure on the cell size though. It seems strange to me that there's only like there's one student here. That seems like it should be omitted. But anyway, finally, we're going to pivot longer. I'm going to say take all the columns that start with number, and the names are going to go to a column called level. So this number level 1, number level 2, number level 3, number level 4, those will all go to their own new column called level. And then names prefix, I'm saying number underscore level underscore. So that's going to give us just the digit of each of these. And then I'm saying the values are going to go to n, but then I also have this one additional one called values p type, where I'm saying n, this thing I'm creating up here, is going to be equal to an integer vector. Okay, so this new column n would be a character vector by default, but we're going to switch it to be an integer. Okay, so all of that gets us here. And then the last thing I'm going to do is I'm just going to arrange by academic year, then district, then school, then student group, then grade level, then level. Okay. And I think it actually already is, but that's just to be doubly sure. Okay. Then we can look at D and it looks like that. Any questions there? All right. Next one. Sum the N across grades for each district within each academic year, student group, and level. Okay, so we're going to calculate, and we're also going to calculate the number of schools, unique schools listed, for each district. All right, so for each district, I want to know how many schools there are, and then I want to basically collapse across grades. So I'm going to sum the ends across grades. Okay, so I take D and I'm going to group by district. And the first thing I'm going to do is compute the number of schools. So I'll just say, what's the length of unique schools? So here's my schools, right? And if I call unique, I'll get all of the different schools for each district because I'm grouping by district. And then I'm saying, what's the length of that? How many are there, right? And so I do that. And we have this n schools here. Let me make this a little bigger so we can see that. So there it is. So the first school district we're looking at has 2 schools in it, okay? And then I'm going to count academic year, district, student group, level in schools. And I have this additional argument, WT, which stands for weight, okay? So I'm going to weight this count according to N, which means I'm going to count each of these, but it's going to be weighted according to this N, which means basically I'm going to be summing the N as I'm doing the count. So rather than counting for each row, I'm summing the N for them. Okay. And that's now going to look like this. All right. And then we're going to pivot wider. So we're going to take the names from student group and we're going to create new columns for those. All right. And those are going to be filled in by the N over here. Okay. So we should have 2 new columns, Hispanic, Latino, and white. And those are just going to be filled in with the N's from over here. Okay. And then I'm going to apply clean names again, because I don't want this to be like that for a variable name. So I clean names, and that fixes that. And then I'm going to drop NA from any that are missing on either of these two columns. Okay. And then finally, I just ungroup, and I'm going to select academic year. So I'm just changing the order. Academic year, then district, then in schools, then level, then everything else, which is just Hispanic and Latino and white. Okay. And that looks like this. Any questions?
Quick question about how you counted the number of schools. Because, I came across an example where, say, for Adrian ST in 2014-15, there was just one school that reported, but in 2015 to 18, there were two schools that reported.
Mm-hmm.
And so, I was just wondering if we split that up, or we just counted.
Yep. So I talked about this a little bit in class. I said that I was fine either way, whether you counted the number of schools by year or by district. Okay. So the way that it sounds like you're talking about is by year within district. So the district perhaps had one school for 1 year, but a different year had two schools. Okay.
Yeah.
So in my case, I'm counting the number of schools they had across the school years. But if you did it by year instead, that's okay. For the plots that we're going to end up using this for later on, we really kind of need it by district, not by district within year, because the year ends up being the x-axis. So that was what I was going for here, but I wasn't really clear enough in my text up here, I don't think. So either way you did it is fine.
Okay.
Any other questions? Okay, so then part B here is going to be achievement disparities. So there's this package, and I know a couple of you on Windows had issues with this, so I apologize for that. I don't know what the issue is. I didn't update this package since last year, and it seems something has changed in the meantime for Windows users because we didn't have any issues before. But so you needed to install this package, and then basically we're going to use these counts right here and these performance levels to essentially create a curve, right? And then we're going to compute the area under the curve, and that's going to be able to be then transformed into an effect size like metric, which is called V, okay? So this is a really neat method because it allows us to get an estimate of the overall basically mean difference in achievement between these two student groups, as if we had the full individual student level data, even though we just have this, what they refer to as Corson data, which is just like basically we have a new fully numeric data that's been categorized into these 4 bins. Okay, so we load Gapper, and then the way I showed you in the example is if we just take the first 4 rows, which is for the first school district, right, for this year, first school district for 2014-15, then we can pass that to estimate V, and then we just supply the columns that we want to use. Okay, so I'm saying white and Hispanic Latino. So it does that, and it tells me that on average, students in the Hispanic Latino group during 2014-15 in this school district scored about 0.8 standard deviations below students who are coded white. Okay, and so what we're going to do then is estimate this average achievement difference for every school district for every year. Okay, and notice what this is returning for us. It's actually returning a data frame. So that means when we're looping through, we can apply map DFR. Okay, so I also asked you to do it 2 different ways. Once with group by nest map, and a second using nest by summarize. Okay, so first we're going to do it by group by nest map. So I'm going to take D, let's look at that again, and I'm going to group by academic year, district, and then in schools. Okay, so in schools should be not repeating across across years if we're doing it this way. Okay, because if we grouped by in schools and it's varying by year, actually it shouldn't matter because we're grouping by academic year here too. So never mind. Either way is fine. But I'm grouping by those mostly so that when I have my nested data frame like this, right, I already have these columns here, and now this is just the rest of the data for that specific combination. Okay, so we have Adrian School District for each of the first 4 years that we had before, then we have Amity, etc. Okay, then I loaded this TikTok library. This is not necessary or expected, but the point of this is just to time how long this takes. So you can run tick, then you have some code, and then you run talk, and then it'll tell you how long it takes. So we'll do that in a second. But I'm going to take this by district data frame, and I'm going to create a new column over here, which I'm calling models. Okay. And then what I'm going to do is I'm going to loop through data, and I'm going to apply estimate V. And then I'm going to add some additional arguments to say white and Hispanic Latino. Okay. Again, I want to emphasize that this is the way that I did it, but this is the exact same as doing something like this. Okay, that is the same. Okay, and similarly, we could do something where we did like function D, and then we could go estimate V D. Okay, both of those are the same. Any questions on that? So this is just passing additional arguments to this function, but this is saying apply this function to each element in data and then pass these additional arguments to this function. Okay. After we do that, I'm just going to select, I'm going to drop this data column, and then I'm going to unnest models. Okay. So before I unnest models, let's just look at it like this. Okay, well, there, oh, couldn't invert Hessian for a couple, that's fine. Okay, so I actually mentioned in the thing that you'll get some warnings about not inverting the Hessian, and that's fine. So this gives us this additional column here, right, called models. And notice that each of these are a data frame. They're 1 by 3. Okay, so this looks like this, right? 1 by 3. AUC, V, and V standard error. Okay, and so we have all of those. And so now we can just unnest this data one, and then, or not data, sorry, this models one, and then we'll have the full thing that we want. Okay, so I can run TikTok on that, and it should get us everything. Okay, so while that's running, I'm going to walk through this one. So this is very similar, but now instead of using group by nest map, mutate map, we're using nest by. Okay, and so nest by is going to do 2 things at the same time. Okay, it's going to nest by the thing that you tell it to nest, but then it's also going to change that data frame into a row-wise data frame. Okay, so if you go nest by row-wise, that's redundant. Okay, because once you do nest by, it's already in a row-wise data frame. So we're going to nest by academic year, district, and in schools, just like we grouped by up here, academic year, district, and in schools. Okay, and then we're going to summarize this time, and I'm saying models is equal to estimate V data. So it's because it's in a row-wise data frame, it's just going to loop through each of those data basically, and then white, Hispanic, Latino, and then this is a little bit weird. But so this, yeah, this is taking longer. 70 seconds. It was taking only like 40 seconds before, so I'm not sure what's going on. But what this models thing is going to look like is it's actually going to essentially say like models $, AUC models $V models $V underscore SE. Okay, so it's gonna essentially break it out just like columns, but it's actually like this weird nested thing. Okay, so to just get V, I'm gonna say models $V, and that will give it to me, and then I can select minus models, and that'll drop all of them. Okay, so that one was 70 seconds. Yeah, so I said 40 seconds. That's what it was before. I don't know why it's taking longer right now, but regardless, this should end up giving me the same thing. So notice in this one, I'm calling it V nest by, and up here it was just V because it came from the estimate V. Okay, so those should be the same, and we can wait for this to run. But in the meantime, are there any questions on any of that? Okay, while this is running, we'll look up ahead to the next thing. Okay, so let's come back over here. After this, I wanted you to reproduce this plot. Okay, and the whole purpose of this is just to show that when we're using nest by summarize, we get the exact same results as we do when we do group by, nest, mutate, map. Okay, so all I'm going to do is left join mods nest by, that's what I'm calling this one, right? And mods. Okay, so I'm left joining those, and it's going to join by all those same things that we had before: academic year, district, and schools. Okay, and then we're going to go to ggplot, put V nest by on the x-axis, put V on the y-axis, add points. I have to make them really big for them to show up on the website properly. Change the color. Then I'm doing geom line, and that's really it. And then we can add some labels if we want to get it to look a little better. So yes, this is basically the same time. So let's look at mods nest by now, and you can see it looks essentially the same. Okay, so when I left join these again, it joins by academic year, district, and in schools. And then we can do the rest of this, and we can see it looks basically the same. Okay, my theme is different, but that's fine. All right. So there's that. Next part, let's go back over here for a second. So I wanted you to create this plot, but I wanted you to actually create it for every school district that we have. Okay, so there's a couple things here, right? We have the name of the school is up here, Bandon School District. So whatever the school district is, we want that to be in the title. Okay, and then this subtitle is going to be the same for each of them, but notice I'm using GG text to get the color in there. And then down here in the note, which is in a caption, I have district included X schools. So however many that ended up being. Okay, so we'll come back here. Oops, not there. Come back here and start to do this. So I asked you to only do it for the first 100. Okay, and then for me, the way that I did this is I wanted to, if we go back here and look again, this says Bandon School District, right? But ours actually, if we look at mods, has SD. Okay, it's just Adrian SD. And then there's all this other stuff additionally after it, like 61 or 4J or whatever, or 5. And those are more identification things, but I don't really care about those. So what I'm doing is I'm string replacing all. I'm saying go through district and find SD and replace it with school district. Okay, then I'm going through district and I'm saying district plus whatever. So anything plus whatever, anything that comes after district, just replace it with district. So basically get rid of anything that occurs after district. Okay, then I'm saying if V is greater than 0, then make it this color. Otherwise, make it this color. Okay, and I'm doing this because later I'm going to do scale color identity. So I could just use these as numbers and then use scale color manual to change those that way. In this case, I'm doing it this way. Okay, so here's V. or come out here a little bit more. Okay, and you can see the directionality there. So they're mostly D3.5, but then we have this 5CA here. Okay, go GG text. And then again, I'm going to do this one by one to start. So I have Bandon. I'm going to figure out how to do it with Bandon. All right. And the way that I did this is I called this numeric as dot factor on academic year. So this is basically going to just be like 1, 2, 3 or 0, 1, 2 rather. Okay. For the, or 1, 2, 3, 4 rather, sorry, for the x-axis. Okay. And then V is obviously my effect size. Okay. Then I'm going to say geom H line at 0, because that's sort of the tipping point for whether one group is above the other, and change the color and size, but who cares, right? And then I'm adding a geom line and I'm making it gray 70, but you can make it whatever. Okay, looks like that. And then I'm going to add error bars, and notice I'm just taking V plus, and this is like way too precise. Q norm 0.025, right? That's going to give me negative 1.96 basically, and Q norm 0.975, that's going to give me positive 1.96. And so I'm just using that to get me my confidence interval. Okay. And then I'm layering points on there, and I'm saying the color is equal to the directionality. Okay. And notice the actual, just for a second. The actual colors are wrong right now, but then I add this scale color identity, and that makes it correct. Okay, and it also gets rid of our legend. And then scale X continuous, so I'm saying the breaks are 1 to 4, which is this thing, right? But then the labels are the unique academic years. Okay, and so we do that, and that gets our actual academic years on there. All right, and then the last part, I have the title where it's Bandon School District here, but we're going to want that to change. And then my subtitle, notice I'm using this span stuff, which is part of GG text, to get those to be correct. And then finally, glue district included, Bandon, and schools. Okay, but ours is going to be different for each one of those. And then I also have to add this plot.subtitle equals element markdown. So that gets us there. Okay, any questions at that stage? That's like the basics of it. Okay. Yep.
Yeah, quick question. Why did you change the years to like factor and then numeric?
Yeah. It's because, so I'm not 100% sure, this might be an old ggplot thing, but I needed this x-axis to be numeric, I think, for some reason, but it's not making sense to me immediately why I needed that now. But, and I'm not actually, so you may not have needed to do that, but as a general rule, you can do this when you want your x-axis basically to be numeric, but you want it to show just like a factor would with these labels. So that's a good question. And I think the answer is probably it was more complicated than it needed to be.
I mean, I think I remember that I did not change it to as numeric, but then I had to use group factor.
Oh,
so
okay.
So I don't know, maybe something related to that.
That might be the case too. Yeah.
Thanks.
Mm-hmm. Okay, so then I'm going to actually do this for the first 100 school districts. Okay, so I have my dists here where I'm just saying my unique ones, and there they all are. And so then I'm going to take my V and filter where districts is in dists. Okay, so that's going to give me a subset of them. And then I'm going to group by district and in schools, and I'm going to nest. Okay, so all of this is going to get me to here. And then I'm going to create a new column, which I'm calling plot. Okay, this is using PMAP. All right, so then I'm going to say PMAP list data, this thing, right? The district and the in schools. And then I'm applying, instead of using the .1, .2, I'm using the function method. So I said function.d.district.in schools. Okay, and so I'm using the dot to just sort of signify that this is different from the actual columns. These are my arguments. Okay, and then I basically just cut and paste the code that I had before, but I put .d here. And then when I come down here, I say .d academic year, right? And then I have achievement gap estimate .district there, right? And then district included .in schools. And I can do that because in schools is just a column out here. And so when I do all of this, what I end up with is a single data frame that looks like this, where we have the data, but now we have a list column of all of the plots. Okay, and we can look at a couple of these. Let me do it down here. I think I had it. Well, I guess I don't. Okay, so we can do this. Look at a couple of these. Let's go plots. Oops, plots. Plot. Let's look at the 5th one. Okay, and it looks like that. Okay. Or we could look at, let me move this again. We could look at the 3rd one. And that's just one of them apparently, so that's less than ideal. That 2nd one. Okay, there we go. Questions? Okay, and then the next part was just replicating it by using nest by summarize. So I'm taking V, ungroup, filter by distance and districts, but then I'm just going to nest by district. Okay, and now I'm going to summarize for my plots. I'm creating a new, or my new thing is going to be called plot. And I just say list, and then I have all the same stuff before, but now I can just refer to those things as what they actually are, the columns that they are. I don't have to do the dot whatever, okay? And otherwise it's the same. So we can look at plots 2, and it looks like this. Okay? Any questions? Okay, the 1 point extra credit was to use Patchwork to put these plots together to kind of show that they are the same. So I load Patchwork, and I'm calling it EC plots. Don't remember why. But so I'm going to loop through the plots for the first method and the plots for the second method, and I'm going to apply a function, which is plus. Okay, that's the one function I'm going to apply. I could also do this, I think, by let's call it 2, where I could go .x plus .y, right? I'm pretty sure that should work as well. Okay, so we'll run both real quick and just double check. So here is, here it is for the first method. For number 4, just a random one. Okay, those look identical. Let's change this to 2, and yep, they look identical. Okay, so we could look at a couple more if we wanted to, but all right. Questions? All right. Finally, I asked you to save these plots in the plots directory and make sure the file names are meaningful. So what I did is I first created a directory which is in content post take home midterm plots. Okay, so mine is much more nested than yours probably is. So I create that, and then I'm going to create the file names. Okay, so I'm going to loop through plots district and split it by SD. Okay, and then I'm gonna, so when I do just this part, this is called string split, right? It's going to just get me the district part. Why am I doing that again? Plots district. And then what is this giving me? I'm not sure this is getting me anything. Let's look at this now. Yeah, I don't think that gave me anything. I'm not sure why I did that. But basically, let's, in fact, just to be sure, I'm going to say dists2, and I'm going to say 2 lower G sub. Well, I'll just copy this. Okay, so this is the part that I really wanted to do. But I'll replace dist with that. Yes, that's going to be the exact same. Okay, so this part is wholly unnecessary. So we'll just get rid of that. And this is much easier. I must have been wanting to do things complicated when I was doing this. Okay, so this is the district. And then I'm going to just append this part to it. So I'm saying achievement gaps underscore whatever the dist is. Okay, .png for the actual file. So now the files look like this: achievement gap Reynolds School District, achievement gap Reedsford School District .png. And then I add on the full file path. So content post, take home midterm plots, files. Okay, so there's files. Each of them is a big long file path and they have meaningful names. And then finally, we're going to go walk 2. We're going to walk through files and the actual plot. I'm going to apply the function ggSave with the width of 6.5 and height of 9. Okay. And then I do that and we can see here's my plots and they all show up. Okay. There's still more of them showing up as we go. So that is it. Any questions on any of that? All right, how did you all feel about this midterm? Did it feel doable? Was it overly challenging? Was it easy? What did you think? Okay, I'm seeing some thumbs up. That's good. All right. Good. So let's go back to the slides then, unless anybody has any last minute questions. Okay. All right, here we go. Let me hide this. Okay, on to functions. This is very exciting. Functions are one of my favorite things in R. They are one of the harder things for, I think, people to get their heads around. So again, as I've sort of been preaching throughout this term, be patient with yourself. If this is not something that you're picking up right away, I wouldn't expect you to pick it up right away. We are spending 2 full weeks on it in a 9-week term, right? So I very much expect that this will take some time, but functions are very, very, very powerful. And it's sort of the thing that I think takes you from being like, yeah, okay, we can use R to be a little more efficient and maybe write nicer code for some things. Functions is the thing that takes you from like, whoa, I can do like anything, like literally just about anything with R if I know how to write functions. Okay, so it's a really exciting jump in your journey. Okay. So functions, anything that carries out any operation in R is a function. I've already mentioned this. So for example, when we do 3 + 5, we are actually applying a function. That function happens to be plus, okay? That's the function that we are applying. In this case, the function is actually going between the 2 arguments, okay? So the arguments in this case are 3 and 5. So we have 3, 5, and the function is in between those, which is unique. That's not normal, but that's what's referred to as an infix function. Okay, the pipe is another example of an infix function. Okay, it's a function that is where the arguments go between the function. All right. What if we wanted to rewrite this though, so it looked more like standard functions? Well, first of all, I guess I should ask, how do you identify functions normally? Like, what's the normal thing that you see when you see a function? Any ideas?
I think arguments, like you must supply a few things in order for it to do something.
Yep, you for sure have arguments. What are those arguments inside of though?
Parentheses.
Parentheses. That's right. So in R in particular, this isn't always the case, but in R, every time you see parentheses, whatever the thing is that's before those parentheses is a function, okay? So we could actually rewrite infix functions so they look more like normal functions. We just have to surround them with backticks, okay? So I could surround the backtick or the plus operator with backticks and then do 3, 5 in parentheses, and we get the exact same result. Okay, so this is a function. There's nothing that really distinguishes it from any other function, except that it's an infix function, which is a little bit strange. Okay, what about this? Do you think we could rewrite this using parentheses to make it look more like a regular function? Just take a second and just think in your mind, what would this look like?
I think we can. We might need nested functions if it only allows 2 arguments.
Yes, that is exactly right. So we would do plus 3.5, and the result of that would go into this place, which would then be added to 7 like this. Okay, so this is nested functions, or using the pipe as we have before, 3.5 and then 7. Okay, so this is not super important. The only reason I'm showing you this is to emphasize that everything that happens in R is a function. Even if it looks a little different, everything that happens, anything that conducts any sort of operation in R is a function. Okay. This is also valid R code, which is weird, right? We have the assignment operator and we say A is defined as 7. We could also write it like this, right? We use the assignment operator and we give it a symbol that we want to bind the object to, 5 in this case, and A becomes 5. So A was defined as 7 up here, and we can write it like this and we get A defined as 5, okay? So this is true with brackets. This is true with everything, okay? Everything is a function. So this is actually one of the things about R that makes people a little nervous sometimes. And I can totally understand why, because some specific things are protected types in R. So there's protected like symbols. So you may have seen me in the past comment on your code when you're saying na.rm equals T with a capital T. And every time I see that, I comment on it and say, you should really avoid using T. Instead, you should use true, all caps, and same with F. You should use all caps false. And the reason for that is because true and false, the full words, are not redefinable. However, T is. So you could take T, just capital T, and define it as false. And that works. And then every time you say na.rm equals T, it will do false, which will be very confusing, right? And if you really wanted to be evil, you could put that in somebody's .r profile, and then that would be the case for them every time they loaded R, and it would make life a nightmare, right? So this is just another example of a devious little bug that you could introduce if you wanted to, which is you could redefine the plus operator, right? So I'm saying if some random number is less than 0.01, then I'm going to multiply the sum of x and y by -1. Otherwise, I'm just going to sum them. So very randomly, every once in a while, when you're using the plus, it's going to be negative, and it's going to make no sense why, right? And so that's a little dangerous. Like it seems like the plus should be protected, but it's not. Same with the minus sign, same with lots of things in R, okay? True and false are two that are protected, though. They are not redefinable. So when in this case, I'm adding 500, this is 1 + 1, then 2 + 2, then 3 + 3, all the way up to 500, right? And then I'm saying how many of those are greater than 0? 494 of them, but 6 of them are not. And they should all be greater than that, right? And apparently my removing of it didn't work here because this should be 500 true. So I'm not sure what's going on there. Maybe I don't know what happened there. So something's wrong there. Anyway. Another thing about functions that is tricky is they are usually objects as well. So everything that conducts any operation is a function. And most of the time, those functions are also objects, okay? So LM is a great example, right? LM is a function, but the actual function is what's inside of LM. LM is just the symbol that that function is bound to, okay? And so we can do things like this, where I'm going to create a new object, which I'm calling A, and it's defined as LM. Well, LM is the LM function. So now A becomes the LM function. So instead of using LM, I can just use A and I get the same exact results. Okay. So what does this all mean? Any operation that happens at all in R is a function, and functions are generally, but not always, bound to an object, okay? Or bound to a name. I say not always though, because we very regularly use what are called anonymous functions when we're looping, okay? So that's what whenever we're doing like lapply, some list, and then we say function X, and then we use X in place there, that's an anonymous function. It's a function that lives within that loop and it never exists anywhere else. So it's not bound to a name, so therefore it's an anonymous function, okay? This is just going through that a little bit more. So here's an example with vapply. I'm saying function X, length, unique, X. This is a function right here, right? This is a function, but it's an anonymous function because it's not bound to a name. It's not bound to any object. Okay. Another possibility, this is strange, but it's actually surprisingly useful occasionally. What we can do is, if we have a bunch of functions, we can actually tie them all together in a list, and then we can loop through the list to apply each function to one thing. Okay, so this is different than normal. Normally we have a thing that we're looping through that we're applying one function to, right? We might instead have one thing that we want to apply multiple functions to. And so then we loop through the list to apply each of those functions. Okay, so it's like sort of flip sides of like reverse things, but they're very different, right? So here's a very quick example. I'm creating a list here. This is a named list that has 4 elements: quarter, half, double, and quadruple. Okay, so those are the names of this list. Each of these is a function. So each of these are function X. So they're just taking one argument, X. And we're taking, for quarter, we're taking whatever X is, and we're dividing it by 4. For half, we're taking whatever X is, and we're dividing it by 2. For double, we're multiplying by 2. And for quadruple, we're multiplying by 4. Okay, so now I have this list called funds, which has 4 different functions in it. Okay, this is definitely kind of weird. But we can do things like this, right? Because it's named, I can do funds $quarter, right? Because this is funds, this is a named list, so funds $quarter, and then I have this function available to me. So if I say 100, I get 25, right? We could also use the double brackets, funds half 100, and I get 50. And then we could also use indexing, funds for 100, and I get 400. Okay, weird, but it works. Does that make sense? So again, I want you to be focused on these parentheses. That's always when the function is sort of starting, right? So the funds is the list, and then within that list, we're accessing the quarter function. And so this is a function. And so then we're using the parentheses.
Is this kind of the basic structure of how like packages are created? Or
Very
is that
rarely.
still completely? Okay.
Yeah. Most of the time, you still have individual functions. The reason you might want to do this, and we'll actually go through an example of this, is if you want to build something like one function that computes the summary of a data frame, right? And so to do that, you might have a group of functions that you want to apply to the data frame. You might want to compute the number of observations, the mean, the standard deviation, the min and max values, etc., right? And so then you might just tie all of those functions together in a list, and then you can loop through each of those functions and apply each of them to the single data frame. Okay, so I've alluded to this already, but if we can store functions in a vector, like a list, then we can loop through the vector, just like any other. So this is exactly what I was just talking about. I'm creating a list here, which I'm calling summary, which has the n, the number of missing, the number of valid, so the number of not missing, the mean, and the standard deviation. Okay, those are the functions that I'm going to apply. And so I can do that to empty cars MPG. Okay, but notice the structure of this. This is very different than what we normally do. Normally, .x is the thing that we're looping over. Well, it is in this case too, but that .x is the function. Okay, so we're looping through summary and we say .x, and then we put the thing that we want the summary of. So it's applying the n to MPG, the number of missing, the number of valid, the mean, and the standard deviation. Okay, but you have to be careful because this doesn't work. This is how we would maybe think to do it, right? But this doesn't work because it's looping through each of these, and then the second argument is supposed to be the function. Okay, but this is not a function. This is an atomic vector. The functions actually live within this list. So we have to sort of subset the list and get at the individual functions this way. Make sense? All right, I've already done that. So this is what per normally does, right? We have some vector, and then we're applying some function. And so it's going to wrap these, each function, each element gets wrapped in the function. Well, that doesn't work in this case because we would be basically trying to take each element of MPG and making that as each of the new functions. Okay, so that doesn't work. But if we do it like this, then we're saying, give me the function and then use that function on this one thing. So this one thing is actually staying constant across here. Okay, again, this is not the most important thing, but it is kind of neat because it allows us to do things pretty efficiently. So I can loop through summary and get MPG, and then I can do it for SIL, etc. And if I'm going to be repeating myself like that, well, then I might want to build another function that does it for all of them. So let's see, do we have time to do this? All right, let's go ahead and try it. Okay, so we'll go for 5 minutes. I'm going to back up here just a little bit. Basically, I want you to copy this code. Okay, and then I would like you to try to build it for empty cars. Okay, empty cars has all numeric columns, so it shouldn't be a problem. And I would like you to try to extend that code that I was doing here to make it work for all columns. Okay, this is definitely challenging. So if you don't get it after 5 minutes, don't worry, but I'd like you to play around with it and see how far you can get. Okay, any questions? All right, go ahead. Okay, so I'm going to start out by just running this. Okay. So now again, summary is a list where each element of the list is a function. Okay, so again, just to emphasize, I could go map df summary, and then I could say .x, and I could go empty cars $SIL. Okay, and that gets me this. So the question is then, if I have empty cars that looks like this, how do I get it to loop through each of these and give me that in return? Okay, so I know I could go map empty cars mean, right? Something like that. And so all I want to do then is just do that same thing, but I just need to now replace the map or the mean function with this. So it's actually a nested loop. Okay. Oops, that apparently doesn't work though. It should work. Let's see. Let me see what I had in my slides. I thought that should work. That's basically what I have. Map. Oh, I have empty cars still here still. Okay, that's why. So I could use the tilde here, but that's going to make things complicated. So we'll function call, and then I'll say whatever the column is there. Okay, and that gets me all of them. And then I could just say map dfr, and that binds them all together. But then I probably want to also add a .id equals var there. Okay, and that gets me all of them. Does that make sense? So again, this was complicated. So if you didn't get it, I wouldn't blame you. It is a complicated loop. The function itself is like none of the functions themselves are very complicated, but because they're stored in this list object and we're trying to loop through that list to then apply each of those functions to each column, we end up with a nested loop. Okay, any questions on that? Okay, moving on. So more readable and better, in my opinion, is to actually write a function. So I have mentioned many times in this class that I would avoid nested loops like the plague, like COVID, if you can. Okay, nested loops are like in terms of computationally, they're fine. There's nothing wrong with them. In fact, your computer does nested loops all the time. But in terms of readability, they're very regularly hard to parse through. Okay, it's hard to figure out what's going on there. So it's much better to abstract away one of those loops into a function. So here's an example where I'm taking exactly that same code that I had before, but instead of applying a specific column, I'm just saying column. And then I'm storing all of this in a new function, which I'm calling summarize call. So I say function column, put this column down here in this code. And now we have a new function called summarize call that will do this thing. Okay, so we could just now say map dfr empty cars and apply that function summarize call with .id equals column. Okay, so this is much more readable, and it is still that nested loop, but it's going to be much easier to say, oh, okay, so each time we're looping through empty cars, each column, we're applying this summarize call function. If I want to know more about that, I go back to the summarize call function and I see, okay, we're looping through summary and we're applying each of those functions to the column. So then if I want to know more about summary, I could go back to that, right? And so it abstracts things away and it makes it much more readable for what each step is along the process. We could also then wrap the whole thing in a function at this point, where we'd say summarize df, function df, the data frame, and I'm going to apply map df. So map df here, but this df goes here, right? And apply that summarize call function with my .id argument. And now I have a function, just a single function, summarize df, which will summarize the data frame for me, okay? We do have some missing data on ozone and solar R. Why do you think that is? Sounds like somebody was going to answer.
Maybe they're not numeric vectors.
They are numeric. That's a good guess. They are numeric. Let's come back here and look though at R. It's way back here. This, the functions we're looping through. What could possibly be going on?
We didn't do na.rm.
That's exactly right. Yep. So for the mean, we're just taking the default mean. For the standard deviation, we're taking the default standard deviation. Both of those have na.rm equals false as the default. So if we want to override that, we need to change that behavior. Okay, so what we would do then is just change that. So it's a function x, mean x, na.rm equals true. Okay, so deep breaths. This has meant to be a high level overview, and part of the motivation, really the main motivation for showing you this, is to show you why we might write functions. So we started out with this really complicated task, right? And we were doing all this stuff, but then we sort of build up. We write one function, then we use that function in another function, then we use that function in yet another function, and by the end, we end up with something that is quite easy to understand. It's just summarize df, right? We're going to summarize a data frame. That's what our function's doing. It's actually calling multiple other functions that we wrote, but that's fine. In fact, that's preferable. That's good function writing practice. Okay, so this is a high level overview. I wouldn't have expected you to write all of this yet, but now we're going to sort of shift from this like up high view into the nitty gritty of the actual particulars of writing a function. Okay. All right, here we go. Function components. There are 3 components to any function. There's the body, which is the actual function part of it. There's the formals, which are the arguments that are supplied to the function. And there's the environment, which is basically where the function is evaluated. So the environment is a little more complicated. It has to do mostly with what's called scoping. And so we will talk about that a little bit later, but we're not going to focus on it too much for now. Okay, so the main thing we want to be concerned about is the formals. So the formal arguments for the function, and then the body of the function. So if you have formal arguments up here, both of those things should appear in the body of your function. Okay, this function actually has what I would call a mispractice for R code, which is it says return Z at the bottom here. Return is fine. However, my practice and what I think of as good practice for R functions is to never use return unless it's being returned early. Okay, so we'll talk about this more later, but this same thing, you could just put Z there without the return. So you could omit the return altogether and just put Z, and it would work exactly the same. Okay, so the return should be used for early return values, not the sort of default. All right, so we'll talk about that more later. Okay, formals. The formals are the arguments that are supplied to the function. So what's one way to identify the formals of the function? Say LM. If we were wanting to fit a linear model to R or in R, and we'd never done it before, but somebody said, okay, well, you can use LM. How would we know what the arguments are that we should supply to LM? What's the first thing that you would do? Gotta be some answer, right?
I think someone put it in the chat. It's $LM.
Oh, sorry, I missed the chat. I don't have my controls up, so I can't see the chat really. Yes, $LM. That's exactly right. So that would be, and that's one good method, right? The other that you could do is ask somebody, right? Or you could look on Stack Overflow or something like that. But what I was looking for is $LM, because that's the help documentation. And if you look at the help documentation, it will always, so let's just go do it real quick. Yeah, I'm still sharing here. So if I do $LM, right here, you will see the formal arguments. That's always the first thing that is shown in the help documentation. So you can see formula, data, subset, these are all arguments to the function. okay? So the help documentation is a great way to get them. You can also actually use a function to understand what the formals for the function are, which is formals, okay? So if I call formals on LM, it will print the formal arguments in a list. Okay, how do you see the body of a function? In RStudio, there's a really neat way, which is you can just hit Command and then click, and then it will, the body of the argument or of the function will pop up. Okay, that's really neat. The problem is sometimes it's not very helpful. So if I do sum and I click on that, that's the entire function. Dot primitive sum. So that's not very useful, right? So actually, if you really want to, this is a good place to start. Command click, and on Windows, it's probably control click. That's a good way to do it. A better way, though, is, or another way, is to just go on, sorry, I keep switching back and forth, is to go find the function on GitHub and then peruse the source documentation. So like, for example, let me think of one. Like, so if I come here and I say dplyr filter, right? And I say, this is what I get. Use method filter, okay? Not very helpful, but what I can do is go dplyr GitHub, and you can see it's here, right? And then I can go to R, and then I can probably find, these are deprecated things, filter, there it is, okay? So when I come down here, I can see this is what's printed for me. But the reason it's printed that way is because there's a bunch of this other stuff that occurs later. So this is the filter method for a data frame. Okay, and this is the main thing that you're going to do. So it says filter rows dot data, and so we can see filter rows. Well, there's that function right there. Okay, writing or reading source code can be intimidating for sure, but I would really recommend it. It's a great way. If you're looking at Tidyverse source code, it's going to be a lot more complicated than other people's source code because it's written with a lot of the time it has a lot of non-standard evaluation stuff, which is hard to understand what's going on. But even so, looking at source code for anything that you're interested in is a good way to A, learn more about the function, but B, learn how to become a better programmer, because the more you're reviewing other people's code, the more you'll pick up on things and understand new and different ways to write things, okay? So those are like the main ways that I would say to use to see the body of a function. However, you could also use a function. You could use body lm, and you can see it there. Okay, the environment. So I don't think we're not going to focus on it too much now. We might later today. I can't actually remember if it's in these slides or the next slides, but we will talk about it more later. But basically, the environment, there's different environments. There's your global environment, which is where a lot of stuff lives. But then there's also environments that are attached to packages, basically. So the namespaces. So if I say the environment of LM, that lives in the stats namespace. Okay, if I did the same thing, in fact, let's do it real quick. If I say environment, it says namespace dplyr. Okay, so that's the environment that it lives in, essentially. Okay, not a big deal for now. Oh, maybe this is the code I was thinking. Okay, this is the code. So we are doing it right now. But this is as much as we'll talk about environments, period. Okay, so here is an example where I have this function called f1. Inside this f1, it defines an object called x to be 20, okay? And then it returns x. But up here, I have x defined as 10. What do you think f1 is going to return? Should it return 10? Because it's defined as 10, x is defined as 10 here, and it's returning x. Or should it return 20? What do you think? How about this? Give me let's see. Give me a thumbs up if you think it's going to return 10, and a thumbs down if you think it's going to return 20. All right. Seeing mostly thumbs down. And that is correct. It returns 20 because of scoping. Okay, so this x lives within inside this function, so it's going to return that. Okay. What about this though? We have x is 1, y is 2, some x and y. Well, this is basically the same, right? It shouldn't be totally surprising that this is, if the last one returned 20, then this one should return 3, right? But it can get a little more complicated in situations like this. So we have x is equal to 2, or is defined as 2 here. X is not defined in the function here, right? But y is defined as 1. So I'm summing x and y. So first of all, when I run F3, take a guess just by yourself. What do you think that's going to return? And then if I try to print y, what do you think that's going to return? Okay. And this is what we get. When I run F3, I get 3 because it's finding x outside of its local function, and then it's getting y from here. But y only lives within that function, so it can't find y when we're just saying do it here. Okay, so the way that I tend to think, it's called lexical scoping with R, is that it's going to look in its immediate environment first. Okay, so in this case, the function. If it can't find that, it's going to go to a broader function. So for example, if you think of a package where a function that lives inside a package, right? And you have something in there that you're referring to. It's going to first look within the function, then it's going to look within the package, then it's going to look within your global environment. If it can't find any of those places, then it's going to throw an error and it's going to say something like object y not found. Okay? So that's what's happening here. It's finding y within the function, but it can't find x within the function. So it looks outside the function to the global environment, and then it finds x there. And so that's why it still works. Okay. This is a function that would be described as not pure because the function depends on things outside of the arguments that are supplied to it. Okay. It depends on x up here. And that's okay. There's all sorts of reasons to write functions that are not pure. And very regularly, I write functions that are sort of one-offs. So they're great and help me be much more efficient in the script that I'm writing, but they'll never be used again in any other script because they depend on things that are within that script. Okay. So basically, I wouldn't worry about this too much. If you end up with unexpected results, sometimes it can be because of things like this. Okay. So yeah, this is all just repeating what I've just said. Okay, so a few examples. These are real examples that I have done before. Okay, so these are fairly complicated, not super complicated, but kind of complicated, more complicated than I would normally do. But I'm just showing them to you, not because I want you to be writing functions like this, but as an example of code that I wrote within a function or within a script that's a function that helps me be much more efficient, but is not going to be ever useful again outside of that. Okay, so this one is called extract grades. This is from a differential item functioning model. And so it takes this argument items, okay? But these items are really only for my items, right? So I take the names of the items and, but what if items doesn't have names outside of this, right? And then I do some stuff. This diff mod part would apply to any of them. Most of this would apply to any of them, but yeah, actually this would generally work. It's just this items thing is a little bit strange, right? Because so I'm creating a data frame at the end here that has the item names, and then the delta, which is what I'm computing here, and then the grades, which is ABC. Okay, and so this was a function that I used to basically take a numeric thing and change it to ABC and have the item names associated with it. So I have to have the item names for it to work, but it really works great for that one script, and I'll probably never really use it again. Okay, here's another one. This one's probably a little more clear in terms of why it would be useful for one given script, but not for any other ever. Okay, so this is a function that just takes a file path as its argument. And we're going to read in the file using read CSV from there. But then I'm going to mutate to do a bunch of stuff. So I'm extracting the content area. I'm extracting the grade. I'm changing it to numeric, all the same kind of stuff that we did before. And then I'm just selecting content area, grade, and everything. And then I'm going to clean the names. Okay. And so then what I can do is I can have some file paths that I have, right? And I can apply this function to each file path, and it's going to read in each of those data frames, but it's going to also do those mutate and clean names and everything to each file as it reads it in. Okay, so but all of this code, most of this code anyway, is very specific to these files. It would not be useful for any other files, but it's still worth writing this function because I'm going to have to do it a bunch of times otherwise. Okay, all right. Another simple example. So please follow along. I'll give you a second to get ready. You can just copy this code if you want to. But we're going to pull out specific coefficients. So we've kind of done this before, but we're going to do it more explicitly with writing functions now. Okay, so I have empty cars. I'm going to group by the number of cylinders. I'm going to nest, and then I'm going to mutate to add a new model on it, right? Where I'm going to say, I'm going to loop through the data, and I'm going to apply this model to it. Okay, so this is what I get in return. Okay, now let's say I wanted to pull out a specific coefficient. For the way I would do this, the way I always do this, is when I'm writing a function, I don't try to just start out by writing the function, right? That's going to be very difficult. And in some cases you can do it, especially as you get more and more fluent with this stuff. But most of the time, it's going to be easiest to still do what I've been trying to preach all term long, which is solve it for one, and then generalize it to a function, and then you can loop that function, okay? So let's pull out just the first model to start, and then we can extract all the coefficients. And it looks like this, okay? Now, if we want to extract just this coefficient for engine displacement, we'd go coef_m, and then we could use brackets with disp, okay? And we get that. Same thing for intercept, all right? So given this, can you write a function that returns a specific coefficient from a model? Use this code as your guide to sort of get started, okay? All right, 4 minutes, give it a try. Okay, give me a thumbs up if you were successful and a thumbs down if you were not successful, or not quite successful. Sideways thumbs are good too. Errol gave me a mountain. I'm not sure what that means. Okay, let's do this over here. So let me actually grab a little bit of code here first. So I'll grab this and we'll just delete this stuff for now. So mods looks like this. Oops, no, no, it doesn't. It looks like this. Okay, and then we looked at this. Oops, I gotta grab it too. I'll just okay, sorry, making me sick probably. All right. So to get just M, I have this, right? And then I can pull the coefs of M. So to get DISP engine displacement, I'd go coef M brackets DISP. Okay, this is the key part. This is how we do it for one. So now we just need to figure out, okay, well, if that's how we do it for one, then what are the things that are varying? Okay, so there are two things that could possibly vary here in our function. What are they?
The model and the name of the coefficient.
That's exactly right. The model and the name of the coefficient. Okay, so what I'm going to do is I'm going to create a function. I can call it whatever I want to call it. Okay, in this case, I'm going to call it extract coef. Okay, then I'm going to bind that to a name, and I'm going to say function, and then I'm going to supply the two formal arguments to it. So I would say model, or whatever you want to call it. It could be anything. You could call it mod or whatever, right? Model, and then coef name. How about? Okay, and then we use curly braces, and then I'm just going to copy this code that I have up here and paste it into here. But then I just replace these pieces. Model is going to be replaced with M, and coef name is going to replace DISP. But this is not really what I want like this, because this is going to always be a string. So what I need to do is remove the string there, and now coef name needs to be passed as a string. Okay, so that's that. Now we test it out. Extract coef M, and let's try DRAT. There it is. Okay, we could go instead HP, and there it is. Okay, questions on that? All right, so now that we've done this, model coef name, wow, I use the exact same things apparently, except I called it pull coef here instead of extract coef, but that is kind of amazing. All right, so now what we can do is we can just go ahead and loop through each of these and pull the different things, right? We could pull the intercept, the engine displacement, the horsepower and drag ratio, and then we can get all of those coefficients here in our actual data frame. Notice I'm using map double in each of these so that I get the atomic vector back instead of a list. Okay, we could also make it slightly more flexible. So since the intercept is a little bit difficult to pull because we have to do these parentheses around it, we have to make sure we capitalize the I. What we might want to do is make that the default. Okay, so any argument that you have in any function can have a default argument. Okay, so in this case, I'm saying coef name is equal to, and then I make it by default hold the intercept. So I just put the code there for intercept. The other thing that is nice about this is we know just about every model is going to have an intercept. Okay, not everyone, you can fit models without intercepts, but most of the time they're going to have an intercept. Okay, so then now because this has this default argument, I actually can apply pull coef without supplying any arguments besides the model, and I'll get the intercept back. Okay, so intercept map double model pull coef. Okay. Again, we could practice it. Yeah. I don't know what's going on there. Okay, so anyway, was I gonna do something else? It seems like I skipped something. All right, I guess we'll just go on. So let's say now, so just actually before I go on, just to re-emphasize, you have to have formal arguments, right? If you do not supply any default argument for that formal argument, any default values for it, then it's what's referred to as a required argument, right? So prior to doing this, I could not use poll coef without supplying the name of the coefficient that I wanted to poll. Okay, now I can. Now I just have to use model. So model is a required argument and coef name is an optional argument. Okay. However, if I want to poll any other coefficient, I could still pass a different argument to coef name and it would poll that one instead of what the default is. Okay. All right. Slightly different problem. And then after this, we'll take a break. What if we want to return all coefficients instead of just one coefficient? Okay. Again, first, we're going to figure out how to do this on a single case, single use case. Okay. So I'm going to use M again, and I'm going to pull the coefs. Here's all the coefficients. Great. Okay. Notice this is a named vector. Okay. So it's got the values down here and the names up here. So the names are those things. Okay. So I could just put those together in a tibble where I say the term is equal to the names and the coefficient is equal to the actual value of the thing. Okay. Can we put this into a function? And I don't have a timer set for this one, but what we'll do is I will set it for, say, 8 minutes just on my phone, and we'll take a break and use that time to try to write this function. Okay, so you basically have a 5-minute break and then 3 minutes to try to write this function. Sound good? Okay, 8 minutes, go ahead. Okay, let's go ahead and get started again. So why don't you give me some sort of feedback, however you want to, on how successful you felt like you were via emojis. So like I'll do a heart because I love it. Okay, not seeing very many. I don't know if it's because people are not back or if people are just not wanting to respond. Here's another one. Okay, well, I got a little feedback anyway. Okay, so this is how I would do this. Let me see. So first, again, just like before, I'm gonna grab this code, right? And this is from M, so that gives me that. And then I'm going to just wrap the whole thing. So I could say poll coefs, or pull all coefs, or extract all coefs, or whatever function. And then I would probably just say model, right? And then inside of here, I would just grab this, put this in here, and then replace M with model in each of those spots. And you could actually do it like this, which is a little fancy. Okay, poll coefs model, and then I could say poll coefs M, and there we go. Okay. Now that we have that function, we can go ahead and loop that through our all of our models, and then we could, of course, unnest it from there. Okay. A little bit nicer version. I'm just basically removing a few things. Okay, so I'm selecting sil and coefs is all, and then unnesting coefs. So here's the cylinder, here's the term, and here's the coefficient. Okay. We could then pivot wider if we wanted, and all of a sudden we have a pretty nice table for all of our coefficients for those models. Okay, when to write a function? This is a very common question. It's like, okay, well, I can write a function, but how do I know when I should be writing a function versus when I should just sort of continue on the way I've always been doing things? Well, a fairly good rule of thumb is that if you're copying and pasting more than 2 and definitely more than 3 times, so if you're copying and pasting 3, 4, 5, 6 times, then you should be writing a function, okay? Writing functions when you're to replace copying and pasting is going to be good for a number of reasons. A, it's going to help your code be more efficient, but B, more than that, it's also going to reduce the likelihood that you're going to have bugs, okay? Because every time you're copying and pasting, you're having to change little things, right? In each copy and paste. And so you won't have to do that if you write a function, okay? And you really won't have to do that if you write a function and then loop, okay? So here's a very quick example where I'm just creating a data frame that has some random data in it. 10 observations from a mean of 100 and a standard deviation of 150. So just like super broad random numbers, okay? Let's say we wanted to rescale each of these columns so that the lower bound is 0, like the minimum value is 0, and the maximum value is 1, okay? We do this by subtracting the minimum value from each of the observations, and then we divide that by the difference between the minimum and the maximum values. So for example, this is one way where I'm showing it sort of step by step, right? V1, 3, 4, 5. The numerator in this case is going to be those values of V1 minus 3. We're subtracting 3 because 3 is the minimum value, okay? The denominator is going to be the difference between the biggest and the smallest. So 5 minus 3, okay? And then the scaled is just the numerator, in this case, divided by the denominator, okay? So again, subtract the smallest value from each observation, then divide that by the difference between the smallest and the largest values. Okay, so here's our raw data, here's our numerator, here's our denominator, and here's our scale data. So if you kind of walk through this, you can see why this works, okay, 0.51. So this might be something that we want to do to each of our columns back here, okay? So we could do it like this. Here it is for column A, great. And then there it is for column B and C and D, right? And this is a very common thing. Like we do this kind of thing a lot, right? We have A minus the minimum of A divided by the max of A minus the min of A. And each of them have the na.rn equals true in it. And so it's a lot of copying and pasting, okay? So as an alternative, we could use, well, so we could use a function. There is actually another alternative in this case that we could do without writing a function, which is we could loop it through using our per skills, okay? So we loop through df and then we just have to write it once, okay? Like that. This is, however, an anonymous function. And so it might be more clear as to what we're doing here if we make it not anonymous and make it a function that's actually bound to a name, okay? So we can instead write a function that lives outside of the loop, and then we can loop that function through our data frame, okay? So looking back at this is basically the thing, right? I want you to think for a second, what are the arguments going to be, and what will the body be? Okay. For the arguments, there's just going to be one formal argument, a numeric vector to rescale. So if we look back at this, we can see this really clearly in this example because this is actually written as a function, right? We have .x. That's the only thing that we're doing, okay? But when you're writing a function, you don't have to call it .x. You could call it num_vector or whatever, anything that makes sense to you. And hopefully makes sense to other people too, okay? For the body, you're gonna have to do something different. So I'm gonna give you another opportunity to try to rewrite what we just did as a function, okay? So 3 minutes, try to rewrite that so that it's a function. Okay, let's do it. So the way I would do this is to start by grabbing the code for 1. So I'm just going to copy this, even though that's not actually everything I want. Get rid of some of this stuff. And then this is really the part that I want, this part, right? So I have A here. What I'm going to do is I'm going to call it rescale 01. Oops. And then I'm going to say function, and I have one formal argument, right? I could call it whatever I want. Pretty regularly with one formal argument like this, especially when it's a numeric vector, is to use x, okay? So I could take that, put it in there, and then I'll just say x, 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 okay? Then I can go rescale 01, test it out. Let's give it a vector that is 3, 5, 9. And we don't get anything. Why is that? Oh, because I don't actually want this there. I don't want to define anything. There we go. 0.33 and 1. Okay. Questions on that? Okay. So there's the body. And so when we create the function, it just looks like this. All right. Now we can test it. And here I've tested it with a few more easy to confirm examples. 0 to 100 by 10, right? 0 to 5, 0, 5 and 10, 0, 5 and 10. Okay. So there's nothing that is wrong with that function as I wrote it. It's totally fine, right? It works. It's great. However, this is sort of like a maximum programming generally. If it works, that's great. And that's the main thing that we care about. However, it can always be better. Pretty much always it can be better. Okay. So we can also improve upon this function by making it easier to read. So one very simple thing is when we're looking back here, we have this na.rm, 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 right? So we're removing NAs from X like over and over and over again. So what we might want to do is actually just remove it one time. Okay. The other thing is that we might not want to calculate things multiple times. So for example, we have the min here. We also have the min here. Okay. Once we've calculated it once, we don't necessarily need to calculate it again. Okay. So here's an alternative version of that same function that might be a little bit more readable. We're going to first just remove all the missing data from X, and I'm calling it Z this time. Okay, so X is the formal argument, but now I'm creating a new object within that function, which I'm referring to as Z. So I remove missing data from it, and then I compute the min and the max of Z. Okay, and then I can just say Z minus the min of Z divided by the max of Z minus the min of Z. Okay, we can test it and it works just the same. Rescale 01B, right? We can also make sure they give exactly the same output. So I'm saying identical, and then I say rescale 01 and rescale 01B, give it the same input both times. It works. I can also just pull some random numbers and check that the output is identical between the two of them. It is. So we're feeling pretty confident at this point that we're in good shape, right? So now that we have this, we can loop through our data frame with mapdf or modify in this case also, and just apply that one function. And there we go. Now our data frame is rescaled. Okay. A little more complex now. What if we want our function? Yep.
And sorry, if we wanted to like create a new variable that was the rescaled version, you would just add like the mutate kind of
Yep.
argument within that last piece.
Yes, exactly.
Okay.
So instead of using map df, we would just do df, pipe that to mutate, and then we'd say mutate, or we'd say, you know, whatever, a underscore scaled is equal to rescale 0, 1, a,
Okay.
right? Other questions? Sorry, I jumped ahead without asking before. Okay, so getting more complex. What if we want our function to behave differently depending on the input? Okay, so for example, a really common one might be, we might want it to do something if the input is numeric, and do something different if the input is a character. Okay, if we're going to do that, then we need to have conditions within our function. Okay, so this is kind of a lot for one day, and this is why I thought it was, this is in particular was one case where I thought it was better when we had class twice a week, because you could have the first day where we talk about functions and introduce them, and then you have a couple days to sort of digest that before we start to get to this. But because it's all in one day now, we're sort of smashing it all together. So we have our basics, right? We can write a basic function, but then very regularly you want to either have checks within your function where you're checking for certain things and you're doing something different based on those checks, or you just have like condition types that you're looking for, whatever. So if you're going to do that, you have your function that lives up here and ends here, but you can add these ifs within it. Okay, so if something is true, so if is dot numeric x, right? So if x is numeric, do something, else do something else. Okay, if you have lots of conditions, you can just nest them. So you can say if this, do this, else if that, something else, do that, and then else means everything else. So if it's red, do this. If it's blue, do this. If it's any other color, do this. Okay. So here's a very simple example where given a vector, return mean if it's numeric and null if it's not numeric. Okay. So function x, if is dot numeric x, if x, the thing that is supplied to the function, is numeric, then I'm creating a thing here called out, which is going to be the mean of x, okay? Else, this should probably be up a level, but it doesn't really matter. But in terms of code styling, it should be up a level. Else, it's just gonna return. So this is what I was talking about previously, where I said return values should only, return should really only be used for early return values, okay? So this is an example where I'm saying return. So if this is not met, then it's going to just return. It's just going to exit out of the function at that point. Okay. But if this is true, it's going to skip this. And so then it will just return out. Okay. And so this return will just return a null because it didn't actually do anything. The function did nothing. Okay. So I say mean2 r norm 12, it gives me the mean. When I say mean2 on some character vector, it just returns null. Okay. So we could use that function within another function, as always. So let's say we want to calculate the mean of all numeric columns in a data frame. So I guess, yeah, we're going to first do this by hand. So we're looking at the MPG data set from ggplot. So you can see it's got some character vectors and some double and some integer and some character and integer. Okay, so if we want to calculate all means, we could say map MPG mean2. Okay, so for manufacturer and model, we get null, of course, because those are not numeric. But for engine displacement, year, cylinder, those are all numeric. So we get the means back. Okay, and then we can drop the nulls. So there's a couple of different ways we can do this. One way is to use map LGL, loop through that means MPG thing, and just say, is it null? And we'll get trues if they're null and falses otherwise. Okay. Then we can use this to subset. So we take our means MPG and we say not is null. So it's not null. Okay. And then we get this, and then we can just say as.data.frame on that. Okay. All right. So probably not surprising, but another challenge. I'd like you to try to go through this same sort of a process, see if you can wrap all of that into a function, okay, where it can be applied to any data frame. And you can test it out on like Palmer penguins or something like that if you want to, after you've written it, okay? 5 minutes, give it a go. Okay, so if we go through this, let's first get our mean to, where'd it go? Oh, there's, okay. All right, so coming back over here, mean to, okay, we get that, and then we test it, that's fine. And then we're gonna deal with ggplot2, I mean, the MPG data set from ggplot2. And so we can do this, right? Get things like that. And then we find the nulls. We're gonna omit them. So there's the nulls. Okay. And then we'll say means MPG not is null. And then we can just say as.data.frame. Okay, so there is that. And now we just need to take this and wrap it in a function. Okay, so the only argument we're going to have here is the data frame, right? So I'll say means df. How about I'll say function df, and then I'm going to basically copy all this, put it into here, but instead of MPG, I'm just going to put df there. That's instead of means here, I'll just say means. How about just means? And then we're going to say is null for means, and then as.data.frame means. Okay, so there we go. And then let's try means df now on Palmer penguins. And that almost works, right? But not quite, because why?
The mean function doesn't have na.rm equals true.
Exactly. So this part of the function is actually fine. It's up here where we have to make a change. And so we'd go comma na.rm equals true. Okay. And then we can rerun that and rerun that. And now when we actually don't even need to rerun that at that point. Now when we run this, we get what we would expect. Okay. All right, so let's go through that with the slides. Here it is, same thing as before, and I even called it the same thing again. That's funny. So df means remove the nulls as.data.frame. And then I think we even have the same issue. Yeah. So we have a problem. How do we fix it? So another way that we can do this is with means to, is we can pass the dots. Okay. So in this case, I've decided for you what is going to happen, right? I have decided that we are removing missing data, but maybe that's not actually what we want to do. What if the user wants to, which might be you, wants to not remove missing data? Well, you've removed that option for them by hard coding it like this, right? So instead, what you can do is a couple of things. You could say na.rm equals true, and then in here, you would just say na.rm equals na.rm, right? The argument to this is going to equal this up here, whatever it is. Okay, that's one way to do it. But then you have to also include na.rm here also. Okay, because that's going to get passed here, and then we'll go na.rm equals na.rm. Okay, so that's one way to do it. The other way, though, is to pass the dots. So you go dot, 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 dot. Dot, 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 and dot, dot, dot. Okay, and this has the added benefit of not only do I have na.rm now, but this is any additional argument that I want to pass to means. Okay, so then when I do this, right, I get NAs, but now I can pass additional argument, na.rm equals true, and it works. Okay, and if we look at mean, we have this like trim argument, which I don't even know what it is. Let's see. It's a fraction between 0 to 0.5 of observations be trimmed from each side of x before the mean is computed. Okay, so let's try that now, where we say trim is equal to 0.5. And I gotta remove missing data too. So I can still keep that there, and then trim is equal to 0.5. Okay, and I get totally different means because that trimming thing is weird. I wouldn't do that, but I think it's basically to remove outliers. But you can see that I can now not only pass na.rm, I can pass additional arguments to mean as well. Okay? Make sense? So this passing the dots is a really powerful way to allow people to still have the functionality of whatever the main function is that's inside of your function. So in this case, it's mean. Okay? And here we go. More examples. Okay, we're not going to do the break, but I also think we're probably not going to get through all these slides because we only have 20 minutes left. So we'll get through as much as we can, and then we'll get through the rest next time. Okay. So to start, I want to talk a little more about purity, and then we're going to talk more about conditionals, and then we'll talk more about return values. Okay. With conditionals, I specifically want to talk about warnings, messages, and errors. Okay. So we use conditionals all the time to do different things within our function, but we might also want to check for certain things. And if it's true, we might want to just stop the function and say, you can't do this. Like you can't compute the mean of a character vector or whatever. Okay. And so we want to return a meaningful, hopefully meaningful error message in return. And then sometimes maybe we don't want to actually stop it. We just want to warn the user, which again might be you, to be like, you know, look out for this thing or whatever. And then messages are just like additional things that you can see there. So we want to understand the concept of purity, why it's desirable, be able to change the behavior of a function. All this is basically what I've just said. Okay, so purity. A function is pure only if it meets these two things, okay? And this is not like technical language, it's just the way that I kind of think of it, okay? So the first one is the output depends only on its inputs, okay? So whatever it can't, the behavior of the function cannot change by anything other than the formal arguments, basically, okay? And then two, it makes no changes to the state of the world, okay? The state of the world being like anything outside of your computer, okay? So even, for example, print, we talked about this, I think, last time, even print actually prints something to your console, right? And so that is making a change, and so that is considered a side effect of the function, okay? So print is a not pure function, okay? And that's what I say there. All right, so common side effects, we've talked about a few. What are some other ones that you can think of? And you don't have to say it out loud, I'll just pause for 10 or 15 seconds, just try to think of a couple, and then we'll list some. Okay, couple examples, and there are more. Print, as I just mentioned. Plot, right? That's another one that was probably close to mine because that was the main one that we were talking about last time. write.csv or write_CSV, anything that you're writing to disk, right? Or reading from disk, right? That is not pure because it depends on the file. So you can read, you can keep the path exactly the same, but the external file might actually change. And so that's going to change the output that is given by that function. Sys.time changes with the time. So it obviously is not pure, right? Options, which changed how your R session works, library, right? And install.packages, it's going to install more packages for you. All right. So side effects are not bad. They're just not pure. Okay. So, so this is all to say, most of your functions, you should strive for purity if you're thinking about writing your function for other people to use, okay? But there's lots and lots and lots of reasons why you might want to write a function that is not pure, and that's totally fine. So purity is a good sort of goal going into it, but if it works out for your specific situation for it not to be pure, that's totally fine too. But generally, functions that are not pure are going to be harder to debug, okay? So if you're having errors with your code and it's because it's depending on some other object that's somewhere else in your script, that's going to be a lot harder to debug than if you have a pure function where it only depends on its inputs, okay? So I don't really actually care about the side effects side of purity so much. I more care about the first one, okay? Its output depends only on its inputs. Okay, this is generally what we're wanting. All right, so that's something to just keep in mind when you're writing your functions. So conditionals. This is from an old lab, and it's, yeah, we're gonna try it. Okay, so imagine we have two vectors that look like this. Okay, and we want to write a function that returns. So the functions, the two vectors have to be the same length for this function. And then I want it to return the number of times that it is NA missing for both. Okay, so for this first element, it's NA for one, but not the other. Same for the second. But then the third is NA for both. So that's one, right? No, no, no. Yes, okay, so this is two. So basically, given two vectors, I want you to count the times when it's NA on both vectors and return that count, okay? So how do you start to solve this problem? Not by writing a function, right? This is probably something that we want to abstract to a function eventually. However, that's not how we're going to get started with this problem, okay? Instead, we're going to solve it on a test case, and then we're going to generalize, okay? So 4 minutes, you can copy these vectors, try to use these vectors and come up with some method that works for counting when they are NA on both, okay? 4 minutes, give it a go. Okay, if you didn't get it in that time, I would not feel bad about it at all. This is a deceptively tricky one. It actually seems like it should be easy, and it actually has a pretty simple solution, but it's very easy to go down a wormhole of like doing all this complicated looping stuff and whatever that you actually don't need to do. This is how I would do it. Is.NA on A, we get some trues and falses. Is.NA on B, we get some trues and falses. So then I just say is.NA A and is.NA B. And then this will return only true when it's NA on both A and B. Okay, so true and false, that's going to return false. True and false, that's going to return false. True and true, that will return true. Okay, so then finally we just sum them. Okay, so I'm going to skip this part because we're just running really low on time and we've done a bunch of this today. But we can generalize it to a function pretty easy then once we get this part, right? In this case, though, it has two formal arguments, x and y. So we're going to say is.NA_x and is.NA_y, and then we're going to sum both of them. Okay. What happens though if it's not the same length? Unfortunately, this is going to introduce some weirdness that we may not be expecting. Okay. So if I say both NA_AB, that's great. It works. Both NA_AA and BB, that gets me 4. That works. But if I say both NA_A and then BB, I still get 4. Why is that? Right? This is very strange. And the reason is because of something called recycling. Okay? So R will do this, and this is I don't think many other languages that I know of anyway do this. So it's a weird R thing, but it can be actually very helpful at times, but it can absolutely lead to confusion. I think probably more often than not, it leads to confusion versus being helpful. So R will recycle vectors if they are divisible. Okay, so here I just have the numbers 1 through 4, and then I have a vector A and B. So A, the letters, right, is of length 2, and the numbers is of length 4, so it can recycle into it. Okay, so the one that's the smaller one just gets repeated for the next one. So you can see this goes AB and then AB. Okay, so that's called recycling. And that's what's going on in that last one. If they're not divisible, then it won't work, right? So when I said that's what's going on, this, in this case, A is being recycled. So we end up with exactly this. This and this are exactly the same because A is being recycled, okay? If they are not divisible, though, it won't work. So 1 to 3 and then AB, it would go AB, A, and then it'd have to have B drop off. So at that point, it just says, no, we're not going to do it. Okay, so it throws an error. So unexpected results. So the recycling can lead to some unexpected results. So what should we do? Well, first, we should probably check to see if they are the same length, and we can return an error if they're not. Okay. So with the checking the lengths, basically we want to check the length of A or X and check the length of B or Y, and we're going to return an error. We're going to stop the evaluation of the function, and we're going to return an error message if they are not the same length. Okay, so basic structure is going to look like this: XY, if my condition, then stop, and then inside of stop, we put some message that we want to say. Okay, so let's go ahead and do this one. This will be probably one of the last things we do today, but try to take this code, so you can just copy it, and then extend it so that it returns a meaningful error message if the vectors are not the same length. Okay, 2 minutes, give it a try. Okay. So this is one way to do it, where I would say if the length of X does not equal the length of Y, then stop. Vectors are of different lengths. Okay, and now we can test this where I say both NA_AB, I get 2, both NA_A and BB, before it would have been recycled, instead we're getting an error in both NA, vectors are of different lengths. Okay. More meaningful error messages. So I'll just probably go through this for the last couple of minutes, but we won't actually get to the point where we're practicing, or maybe I'll just show the answer. Okay. One thing that we could do is state the lengths of each. Okay, so we could say the vectors are of different lengths. The first one is 5 and the second one is 7. Okay, so they're not going to work. So yeah, and apparently I just already had that here. So in this case, now I'm saying if the lengths are not the same, right, then first I'm going to calculate the length of each of them. So I'm pasting together x is equal to whatever the length of x is, and y is equal to whatever the length of y is. And then I'll say stop, vectors are of different lengths, v lengths, and you see we get error in both in A. Vectors are of different lengths, x equals 7, y equals whatever it is, 14, probably. Okay, it's running off my screen. Okay, cleaning up just a bit. We often don't need to echo the call. So back here, notice it says error in both NA, AC, A, and then BB, right? Vectors are different. Like this is echoing the call. And we often don't need to do that because it's clear which function that you have just called. And so to do that, you would just put this call dot equal to false in the stop message. Okay, so within stop, you have this call dot optional argument, and then it just returns something like this. Vectors are of different lengths, x equals 7, y equals 14. Okay, there are also, if you want to just do quick error messages, you can use stop if not. I use this if I'm doing something that's just for me internally, and it's not like something that's going out to the users. So for example, z-score, stop if not is dot numeric, right? And then when you try to z-score something that's not numeric, it'll just say is dot numeric is not true. Okay, that's a not very good error message, but it's a very quick way to do a check. Okay. All right. All right, I'll just mention this real quick and then we'll call it good for today. So we'll start on slide 100 basically, but we'll probably review a little bit of this next time. Okay. So if you want to embed a warning, all you have to do is swap out stop for warning, and then the rest will work fine. And the reason we might want to do this is actually recycling is a perfect example of when a warning is probably preferable to an error, right? So if one is of length 4 and the other is of length 8, it could recycle into it and it could be just fine. And it's possible that that's what the person who did this meant and wanted to do, but it's also possible that they weren't thinking about recycling and they're going to get an unexpected result. So what you could do is check to see if it's been recycled, and then you could throw a warning to get the person to sort of double check their results instead of an error. So it would still return the results, but it would return the results with the warning error or warning message. Okay. All right. So that is it for today. We didn't get through everything, but that's okay. Next time we'll pick up here and we'll finish and we'll do the slides for next time, but we will also have our third and final lab for next time. Okay. And then we'll be all functions next time, and then we'll switch to Shiny for the last 2 courses, and then your final project will be due. Okay. Okay, thank you all.